Imagine we're standing on an airfield, looking at a massive jet. It weighs hundreds of thousands of pounds. What on earth is keeping that much metal suspended in thin air? It's not magic. It's a beautiful dance between a solid object and a moving fluid. We call this force lift. To understand lift, we have to break it down into a few basic truths. At its simplest level, lift is the net force acting perpendicular to the direction of the wind. It's a game of push and pull. Every fluid exerts pressure. If you make the air push harder on the bottom than on the top, the wing goes up. Think of a crowd. If people below you are packed tight and pushing up, but the crowd above is sparse, you'll be lifted. How do we get that pressure difference? We use the Bernoulli equation. This isn't just a formula. It's a statement about the conservation of energy in a flowing fluid. If we assume the height change is negligible across a thin wing and divide by volume, we get the classic Bernoulli constant. This shows that where velocity is high, pressure must be low to keep the sum constant. We shape a wing so that air traveling over the top moves faster than the air underneath. The air on top is racing and becomes relaxed, creating low pressure. The air on the bottom is slower and bunched up, creating high pressure. But why does it move faster on top? In perfect air, the flow would try to whip around the sharp back edge to meet the air on top. But nature doesn't like sharp turns. Air can't make that hairpin U-turn. You've felt this yourself by sticking your hand out a car window. Tilting your palm up, the angle of attack increases lift. The air is forced to deflect downward more sharply, creating a stronger pressure difference. But you can't tilt forever. If the angle is too steep, the air can't stick to the top anymore. It becomes turbulent and breaks away. This is a stall, lift vanishes, and drag takes over. To fly slowly, like during landing, pilots use flaps. These increase the wing's surface area and curvature, maximizing lift when the speed is low. In the real 3D world, wings have ends. High-pressure air from the bottom leaks around the tips to reach the low-pressure top. This creates spinning spirals called wing-tip vortices, which create induced drag. To fly, we exploit physics to create a lopsided environment. By using the airfoil shape and the angle of attack, the atmosphere literally pushes the airplane up. It's a constant tug-of-war between lift and drag.